Hey y'all, I'm Sunny Shell, and tonight I am super excited because I have Ethan Siegel back on, and we're going to be talking about living on Mars. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven.
Jefferson laid great stress on it. It wasn't enough, he said, to enshrine some rights in a Constitution or a Bill of Rights. The people had to be educated, and they had to practice their skepticism and their education. Otherwise, we don't run the government. The government runs us.
Hey everyone, I want to welcome back Ethan Siegel. I absolutely love when you come on. What have you been up to since we last spoke?
Oh my goodness, there has been so much that's very exciting. I don't think I've been on since 2023. So, in this new year, for those of you who have not been paying too much attention, we have a new children's book out that I am a co-author of. It's called The Littlest Girl Goes Inside an Atom. And later this year, I will have my very first book coming out that is published by National Geographic. It is their first book on the James Webb Space Telescope and all of the amazing new discoveries that is making and what we're finding. And I have authored it. We have an introduction by Brian Greene. And I just checked. You guys are the first to know. It is up on Amazon, and you can bookmark it to know, to be alerted to when it comes out. The scheduled publication date is October 8th of this year.
Fantastic. That's so exciting. I think we can put that link maybe in the chat and that kind of thing.
I'll grab you one right now, and I'll send it over.
Oh, awesome. So I want to thank all of our viewers because we're on a different night than we normally are. And I know that can be confusing sometimes for our viewers, but we wanted to make sure we got Ethan on. And so I want to just thank all of you for letting us kind of maneuver things and do things in a little bit of a different way, right? So,
yeah. And thank you, Sunny, for being flexible. You know, I have some travel plans and unfortunately some medical events coming up, but I wanted to make sure that we had an opportunity to get back on that and to say hi to you and all your beautiful listeners and readers out there before I was unavailable for a little while.
Yeah, well, we hope that everything that you do, your travel, medical, everything goes well, safe, happy, healthy.
Thank you.
All right, so let's go ahead and jump in. Now, I said we're going to be talking about living on Mars, but we're actually going to be talking about living on planets, on any habitable planet. And so, to kind of get us started, I was wondering what habitable zone planets are the best candidates for life?
All right. So this is a really big question, right? Because we assumed back before we started discovering a lot of these new planets out there, before we started discovering what we call exoplanets, we assumed that stellar systems in general, stellar and planetary systems, would be similar to our own solar system. And we assumed, oh, well, you have a star, and when you get the right distance away from that star, not too close and not too far, right, then you'll have the right conditions, right temperature to have liquid water on your surface. So assuming you're an Earth-sized world with an Earth-like thin atmosphere, what temperatures and distances, what temperatures are your star, what temperatures will you need at a certain distance from your star to have liquid water on your surface? And we assumed that would be the ingredients for life. That would be the recipe. And we also assumed that other stellar systems would be like ours, where inside in the inner solar system, you're going to have rocky small planets. And then as you get farther out, you'll have these big gas giant planets. And we thought that would be the template. Now that we've seen other solar systems, other stellar systems, and we've discovered over 5,000 confirmed exoplanets now, right? That was a milestone we hit a little over a year ago. Now we're saying, oh boy, okay, some of our assumptions way bonkers wrong, right? Planets can be any mass, any size, and any distance from their star. The formula that we have for inner rocky worlds and then outer giant worlds, not universal at all. That's not even a relatively common configuration. Also, we assumed small worlds like Earth, Venus, Mars, and Mercury versus large worlds like Jupiter, Saturn, Uranus, and Neptune. No, it turns out that perhaps even the most common planet out there is of an in-between size, what people call either super Earths or mini Neptunes. Or if you're a fun-loving alcoholic, maybe you call them Neptinis.
I like that.
Yeah, this is what's out there in the universe. The idea of a habitable zone is still saying, okay, let's assume that you have a small rocky planet with a thin atmosphere and you want it to have liquid water on the surface. We still use that same idea in what we talk about as the habitable zone. But this is only, what we think of as a conservative area, right? We think that early on in a stellar system's history, stars are cooler and they heat up as they age. So maybe early on in our solar system's history, Venus was a good candidate for life. We also think if Mars was just a little more massive and had a little more internal heat in its core, maybe it could still be potentially habitable today. When we look at the evidence on Mars, we find that it probably had liquid water oceans for 1 to maybe 1.5 billion years before, the atmosphere was stripped away and the planet dried up. So we say habitable zone because it's based on assumptions of what happened here, but the truth may be much weirder than that. It may be that farther out in a solar system or in a stellar system, farther away from the sun, maybe you're more likely to have a giant planet with large moons around them, and maybe one of those moons is the most likely habitable candidate. Maybe something like Jupiter's Europa or Saturn's Enceladus or even Jupiter's Ganymede or Neptune's Triton might be a better candidate for life than a world like Venus or Mars, analog in another stellar system. Another thing that's kind of weird is we think, oh, our sun, that's an average star, right? Most of us learn that the sun is just an average star. No. If you went and you said, I'm going to collect all the stars in the universe or in our galaxy or that we've surveyed and put them in a big bag and sort them, right? And say, here are the low mass ones. And then you get bigger, 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 high mass ones. Where does the sun fit? It turns out only about 5% of all the stars that we know of are bigger, more massive, and hotter than the sun. 95% of stars are the other way, smaller, cooler, and lower in mass. That also means they're longer lived. And this is actually a problem because most of the small planets we found, most of the Earth-sized planets that we found, they're around these small, low mass stars. And people want to know, well, are those worlds habitable? And my answer, right, which I've changed as I've learned more information, is probably not yet. And the reason is when a star is very young, it's very active. It flares all the time. It emits X-ray radiation. It has coronal mass ejections. Sometimes it even has these colossal events called surface mass ejections that can completely strip a planet's atmosphere away entirely and certainly would irradiate and be potentially very damaging to any life that was attempting to live on the surface of that world. Well, guess what? Around our sun, right, that phase only lasts a few tens, maybe hundreds of millions of years. Then it dies down and all the worlds become potentially habitable without worrying about those catastrophes. Around higher mass stars, that process is even faster. The problem with the high mass stars is they live fast and they die young. So if a star's twice as massive as the sun, instead of living for 10 or 12 billion years, it's only going to live for like 1 to 1.5 billion years. Not maybe enough time to produce interesting life where like we think of ourselves as interesting life. The lower mass stars live longer, but the downside is it takes them longer to settle down. So when you look at the red dwarf stars, or what we sometimes call the M-class stars in the universe, these stars aren't going to live 10 to 12 billion years like the sun. They'll live hundreds of billions of years, maybe even trillions of years. The longest ones might even live for like tens or hundreds of trillions of years. But the problem is we only live in a universe that's 13.8 billion years old. These stars have not had time to settle down where they stop flaring and stop doing all this monstrous mess that they inflict on their orbiting planets. So it's possible that these M-class stars have planets that are habitable or even inhabited, but we have reasons to disfavor that. And this is something that we've only newly learned in the last few years from the science of astronomy, planetary astronomy, and exoplanet sciences. So that tells you what the habitable zone is, and it also tells you why you shouldn't trust it.
So this has struck a question. It's off of the questions that are already prepared, but it kind of got me thinking. What is it that allows a planet to have an atmosphere? And if a planet loses the atmosphere, can they regain it naturally?
Oh yeah, you super can. The Earth, we lose atmosphere all the time. But we also make our own atmosphere because we have a volcanically active planet. Volcano activity spews gases into the atmosphere: nitrogen, carbon dioxide, sulfur dioxide, all sorts of gases. Carbon dioxide is a great gas because it, as we know from our own planet, it helps trap heat, which is useful for a planet, right? To say like, if I don't have an atmosphere at all, what's going to happen? I'm going to get really hot during the day. And then when I turn around, so it's the night side, I'm going to get really cold. I'm going to radiate all that heat into space. We normally think about an atmosphere. We talk about the term greenhouse effect. Very few of us own greenhouses, but all of us own blankets. I think of the atmosphere like a series of very thin blankets. And if you're cold, what do? Oh, just put another blanket on. Put another blanket on. It'll make it warmer. That's what happens. That's what your atmosphere does. It's like putting a blanket around your planet. It keeps the temperature warmer, but it also keeps the temperature stable. So if your atmosphere circulates around your planet pretty quickly, whether your planet's spinning fast or not, even if the atmosphere just circulates quickly, you can keep the planet at a stable temperature. So there may be planets out there beyond the habitable zone that have thicker atmospheres, maybe not like Neptune thick atmospheres, but thicker than Earth atmosphere, that they have enough blankets that they're like, no, life's doing great on this world. Don't mess with us and don't count us out either.
Oh my gosh, my brain is now having all these different questions, but I'm going to try to stick on topic and not go too far out. So let me ask you, when we have something like 5,000 exoplanets that we've so far discovered, how can astronomers then prioritize which ones to search for life on?
Okay, so once you've identified a candidate planet, right? So you get like the two main ways we do it. There are other methods that are going to be more successful in coming years. There's going to be things like direct imaging. There's going to be things like microlensing. These are going to be great down the road technologies. Right now, we have two main ways of detecting them. One is we watch a star. You look at a star in the sky, but you don't just say like, I'm watching a star. What you do is you measure how this star moves over time. Because if this star has a planet orbiting it, it's not just, planets go around stars. It's that planet-star systems orbit their common center of mass. So if I have a massive planet that orbits around this star, then that star is going to do what we call wobble in its orbit. It's going to make these tiny little ellipses. And we can't detect the side to side or up and down motion, but we can absolutely detect when it moves towards us and when it moves away from us. Because when it moves towards us, just like when the ice cream truck moves towards you, you hear that Pop Goes the Weasel tune higher pitched. And when it moves away from you, you hear, oh, it's lower pitched. Well, for light, it's not the pitch that changes, it's the color. Light, something that moves towards you and emits light is going to have its light slightly shifted into the bluer part of the spectrum. And something that moves away from you is going to have its light shifted into the redder part of the spectrum. So when you see that blue, red, blue, red pattern, that tells you, oh, I must have a planet. And the planet has to be orbiting with this mass and this period and this orbital distance from the star. That's how you know you have a planet. Another way we do it is we say, well, once in a while, yeah, planets are going to orbit like this around the star, fine. But once in a while, you will get an alignment where a planet passes right in front of your line of sight and appears to pass directly in front of that star's disk. And when it does, it blocks a portion of that star's light. This is what we call the transit method because it appears to transit in front of the disk of the star itself. When it does that, brilliant idea here that they had, when it does that, a little bit of that star's light, yeah, a lot of it will be blocked by the planet. Most of it won't be interfered with by the planet at all, but a little bit of it is going to filter through that planet's thin atmosphere in a ring. And when you take a look at that little part of it, that little part of light, then you can do something called transit spectroscopy, where you say, ooh, this starlight is passing through the planet's atmosphere on its way to me. And all of the atoms and molecules in the planet's atmosphere have a chance to absorb that light. So what can I see? What can I see when I look at that? What types of molecules are there? What types of atoms are there? And that's where the search for life gets interesting, because you can say, oh, if I see an atmosphere that's mostly made up of nitrogen and oxygen, that's like our atmosphere. That's possibly very interesting because we know for billions of years, Earth had a negligible amount of oxygen in its atmosphere. It was only life processes that created the oxygen is the second most abundant molecule in the atmosphere. If you go and you say, oh, I want to find what else could there be, and you can see these carbon dioxide levels rising and oscillating with the seasons, you could say, oh, goodness, they invented fossil fuels on their planet. They figured out how to burn their old trees that were like this. You can say, oh, goodness, I detected chlorofluorocarbons in the atmosphere. They invented hairspray in the 1980s. This is great, right? So these are, believe it or not, these are actual examples of what we could call biosignatures, or signatures of life, that life would produce these things. So yes, today we really only have the stellar wobble, or sometimes called radial velocity method, and the transit method to primarily detect these exoplanets. But future technology will involve taking transit spectroscopy of starlight that filters through these planetary atmospheres. And in the future, telescopes like NASA's upcoming Habitable Worlds Observatory hope to directly image these planets themselves so that you can block out the star's light and get that faint little signature of the planet on its own. And then you can measure its light directly and say, what color is this planet? When it rotates, do I see evidence of continents and oceans? Do I see clouds in the atmosphere? What color is the world? If I do have continents and ocean, do the continents green and brown with the seasons as the planet orbits its parent star, right? These are questions that we've never answered for any world outside of our own solar system. that we are developing the technology to make those measurements, I'm excited within our lifetimes.
That's so cool. I am so excited. It's like your childhood dreams and wishes coming true in real time. Um, Earlier, I put this up. I want to thank Dan D for a $10 super chat. And he says, nothing can block Sunny out. Thank you. I appreciate that. Very nice. We have a question from Skeptic Haven. So it's in two parts. So I'll start to the first one. Blocking out the sun, then looking for planets around it. Here's part two. Is that a useful way? Is that a useful way? I think that my cousin Misty made a mask thing that does that on James/Web.
Well, way to go, Misty. There are two ways that we know of to do this. The main way that we use this is there's a technology called a coronagraph. And what this does is we normally use it for the sun. You'll say like, oh, if I'm looking at the sun is too bright and everything gets lost in the glare. But if I take a little circular obstacle and I hold it up to completely block out the sun's light, then I can see all the stuff that happens around the sun, including the sun's corona. That's why it's called a coronagraph. But if I apply this technique to other stars, I can say, well, if I know there's a star right over there, and I just put the little sphere to block the star's light, then maybe close by it, if I can block the star's light perfectly enough, I can maybe see those planets that are close by it. This is a very challenging optics problem. If you just made a spherical disk and said, I'm going to use this to block the light, you get interference and diffraction at the edges of that sphere. So you can only see something that's maybe 0.01% or 0.001% as bright as the star. But there are new coronagraph technologies that they're developing. The JWST, the James Webb coronagraph, is better than the coronagraph that's on Hubble. They are building a better coronagraph for the Nancy Grace Roman Space Telescope. That is NASA's next flagship space telescope that's going to launch. But they're hopeful that they'll, and that's going to get up to like 1 part in 1,000,000 to 1 part in 10 million. So you can see fainter.
Wow.
If you wanted to see Earth, though, around a sun-like star, you need to get up to a factor of like 10 to 100 billion. That's 1
Wow.
part in 10 to the 10, 1 part in 10 to the 11. Coronagraphs may be able to get there. They are working on developing coronagraph technology so that we can have exactly that happen when we fly Habitable Worlds Observatory. But if we can't, there's an alternative approach called a star shade. This is not a spherical obstacle. This is like a pinwheel shape. It's a mathematical object designed that you would fly it tens of thousands of kilometers away from your space telescope. And you would position it so that when your space telescope points at this star shade, it blocks the light from one specific star. But in those little ridges between the pinwheel, you can still see the light from the planet. And that can be theoretically optically perfect. You can achieve contrasts of 10 to the 10, 10 to the 11, even 10 to the 12. And so if the coronagraph is not good enough to directly image the planet, it's more expensive, but a star shade will be.
Wow. Okay. So can you tell us a little bit about the TRAPPIST-1E?
Oh, everyone loves this TRAPPIST system, right? So a few years ago, we discovered this really awesome system called the TRAPPIST-1 system. TRAPPIST-1 is a red dwarf star. It's one of those M-class stars that I warned you, it's probably flaring too much to, not strip away the planet's atmospheres. But right now, we know of 7 different planets that orbit this system. They all orbit very close to the star itself, all interior to Mercury's orbit. But because this star is so faint and so small and so low in mass, the inner 2 planets they must be baked and barren and Mercury-like. The outer planet, you just name them B, C, D, E, blah, 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 until you are done finding them. H is the farthest one we found. H should probably be cold and frozen, colder than Mars is in our own solar system. But those intermediate ones, E and F in particular, they might be in what we consider their star's habitable zones. So this is a star just 40 light years away. And these 7 planets do all transit their star. They pass in front of the star's disk relative to our line of sight. So we have looked at TRAPPIST-1b and TRAPPIST-1c with the James Webb Space Telescope. And what JWST is seeing is these are pretty consistent with having no atmosphere, although they could have thin carbon dioxide atmospheres that don't show up. But E, F, these are the worlds that we think, well, look, we have lots of reasons to think that maybe this class of star doesn't have life on it yet, but it's just 40 light years away. And these are planets that are in what we call the habitable zone, which means if they do have Earth-like atmospheres, then they do have the potential to have liquid water on their surfaces. This is a question that in the next generation of observatories, which means when we get 30-meter class telescopes on the ground, or when we get Habitable Worlds Observatory up and running, if those worlds have interesting atmospheres with, I'll call them bio hints at this point, because I don't want to be too confident, but if we find, interesting molecular signatures on these worlds, these could be candidates for life that are in easy reach of us. So I think that's really an important thing when we're looking out at all these possible places where life could be in the universe. Look at the lowest hanging fruit first, because if you can grab it, it's worth looking at. Even if we think, oh, we have some reasons, maybe we don't think it has life, or maybe there are reasons life can be disfavored, you miss 100% of the shots you don't take. Look and find out, because I don't want to say, well, theory predicts that. No, I want to know. Make that observation. And I'm a theorist. I still want to know. Get that data.
Yes, I love it. So I just want to ask you a quick question, because as I was looking at that graph that you had up, you depicted TRAPPIST-1e kind of in a greenish color, whereas the Earth is more of a bluish color, which we have a lot of water on our planet, but the E planet is very greenish in the color. So that made me wonder, first of all, if there is something that indicates as far as what's on that planet, and secondly, if it's not water, is there something else that could potentially produce life? Maybe not life that we, that's like us, but maybe, because we know that there are things that are alive on our Earth that are not exactly, they're like down in the bottom of the ocean where there's a lot of the volcanic gases that come out, and you think, well, nothing could survive there, and then you find something that does. So,
all right. Well, I've got good news and bad news. The good news is, yes, we don't assume that all life that's possible in the universe is going to be like life is here on Earth. We don't say, oh, you need liquid water and you need carbon-based life and you need a Krebs citric acid cycle and you need photosynthesis, and there's no reason to believe that the way life happened here on Earth is the only way that life can happen in the universe. We don't know how life got its start. We don't know, let me make an analogy. I look at life as a lottery. Earth got a lottery ticket, and clearly we won some sort of prize in this lottery because we have life on our planet, and we have human beings on our planet, and we have mammals and reptiles and birds and all of these things. And if you look in the historical record, we have a bunch of things that we didn't have, right? That we don't have now. We had trilobites and dinosaurs and flying reptiles and ammonites and cyanodonts, and we had all sorts of creatures, living organisms that are now extinct. How else could life have arisen, right? We assume it's chemical based. We assume it's made out of atoms. We assume it has to have some mechanism by which it metabolizes energy or nutrients or resources. We assume it has to have some way to replicate itself. But that's really it. We don't we try and keep our minds open because we know we'll know what alien life is when we find it, but we don't want to overlook it because we weren't casting our nets wide enough. So we keep our minds open to, hey, maybe Saturn's giant moon Titan, which has liquid methane on its surface, maybe that's a good candidate to have life. Maybe the subsurface oceans of a world like Pluto, which might not have liquid water as much as oceans of liquid nitrogen or liquid carbon dioxide, right? It's not just water is the universal, like, no, lots of things make liquids in the universe, and keep your mind open to what they could be. Maybe life is more common around hydrothermal vents than it is on the surface or at the interface of ocean and land. Right? These are possibilities. But the other part of your question about, like, well, why did we color the TRAPPIST planets with those colors and color our solar system with the colors we did? That's just art. Other than the planets in our solar system, we don't even know what color those other planets are. That's not part of the information we've been able to get about them just yet. You can with direct imaging. When you get to direct imaging, you will know what color those planets are. But right now, with the technology we have, the only planets that we can get direct imaging for are those large gas giant planets that are well enough separated from their parent stars. So things like super Jupiters that are way far away, yeah, we can directly image those and say, oh, I can see what color that is. But for a world like the TRAPPIST planets, we don't know what color they really are.
Well, I love artistic expressions, so that's okay with me. I'm looking forward to hearing what we might find at some point. What
I'm
those
very
planets
much
would
looking
actually
forward
look
to
like.
the day where we can recolor them their actual colors.
Yes, absolutely, absolutely. We're at the halfway point. I just want to remind everyone, if you're liking this show, you like this content, remember, just hit the subscribe button, share, hit the bell so you can be notified when we have new shows coming out. Okay, so the next thing, we talked about TRAPPIST 1E. What about Wolf 1069?
Ooh, this is a fancy one. So Wolf 1069 is the name of a star. And this is a star whose exoplanet, Wolf 1069b, we just discovered last year. This is a new exoplanet. So when I told you, like, we found 5,000 exoplanets, this is in the plus. This is after 5,000. So we've got more now. I'm going to show you, I've got a little I've got a little screen share that I think I can do over here, maybe. This one, I think, is right. All right. So maybe you can see my screen. I don't know. Oh, look at that. So there is this planet, Wolf 1069b, that is, you can see this little green band. Wolf 1069 is a star that's 31 light years away. So it's 9 light years closer than the TRAPPIST-1 system is. And it has an exoplanet around it. This exoplanet, they have colored this nice red color and they've put clouds on it, but we don't know if any of that's true. What we do know is that this planet is only a little bit larger than Earth. It's only 8% larger than Earth in radius. and it's only 26% more massive than Earth in terms of its mass. We call this a confirmed planet because we have observed it transiting, and we have observed that star wobbling back and forth. That's how we know both the mass and the radius. So you take a look at this and you say, ooh, that's really interesting, right? So let's what could this mean? Now, yes, this is still an M dwarf star. You can get information about this star. And what you can find is that, well, I wish this had more information than it does. But the truth about Wolf 1069 as a star is it is the sixth closest Earth mass planet in the habitable zone of its star to us. So that's pretty impressive. And when we look at the star, Wolf 1069, we say, actually, this is much lower in mass than the sun. It only has about 1/6 of the sun's mass. But here's the crazy thing. If you think, well, the sun is 6 times more massive than Wolf 1069, how many times brighter do you suppose the sun is than Wolf 1069? You want to take a guess? I won't make you guess. It's mean. All right. The sun is about 350 times brighter than Wolf 1069.
So way off in what I was thinking in my head.
Yeah. So this is a wild thing, right? It's small and it's lower in mass. It's about 18% the sun's mass, about 17% the sun's radius, 17, 18%. But it's so much fainter. It's so much fainter. And it's also young, right? You take a look at a star like this and you say, how old are you? And the answer is, well, it doesn't matter because you're not old enough compared to the age of the universe. You're still flaring. You're still in this active stage where any life on that planet is going to have a difficult time. But that's okay. Difficult doesn't mean impossible, and it's still a place that's worth looking. This is going to be a great candidate planet when we get direct imaging to say, what color is it? What type of atmosphere does it have? Does it have any liquid on its surface? We're going to learn a whole lot about this. You have to recognize that it's easier to see little planets that orbit little stars. The more massive and brighter your star is, the easier it is for that planet to get lost in its glare. The reason we're so excited about all of these low mass Earth-sized planets around the red dwarf stars is because we can find them with current technology. It's really hard to find an Earth-sized planet at an Earth-like distance from a sun-like star. We know of very few. Maybe there's one in the Alpha Centauri system, right? Because that's the closest star system to Earth. It's only 4 and change light years away. The next sun-like star is more than 10 light years away. It's like more than 2.5 times farther away than that nearest star is. So you go farther away and it gets harder and harder and harder to see a separation that's so narrow on the sky. So part of the reason we get so excited about these planets around red dwarf stars is because we can detect them now. And so, of course, we're going to ask, does it have life? I doubt it, but look. And the more you look, the more you learn, okay, if this doesn't have life, then what's the next step? And what's the next more difficult? And it's through this, if we keep this up, if we don't, a lot of people take this attitude, Sonny, I'm going to vent for a little bit. A lot of people take this attitude that if the first thing you can see doesn't have what you're looking for on it, then it's easy to give up. It's easy to get discouraged. It's easy to say, oh, this is going to be hard. I don't want to do it. Astronomers and astrophysicists, we're not like that. We say, no, look at all the chances we got. Look at how successful we were here on Earth in winning the cosmic lottery. We don't know that we're the grand prize in the cosmic lottery. There could be more habitable planets. There could be planets that have had life succeeding and thriving on them for many billions of years, not just 4 billion years like here on Earth, but maybe 7 billion, maybe 9 billion, maybe 11 billion, right? The universe has been around for 13.8 billion years, and arguably the very first habitable planets, the very first inhabited planets, could have arisen when the universe was just about 1 billion years old. If some of those are still around, which they would be around a star that was just a little bit less massive than the sun, maybe those civilizations are unfathomably advanced compared to what we think of. So don't rule out hope because it didn't happen in the first system you looked at, or the first 10 or the first 1,000 system you looked at. Life is out there. It's guaranteed to be out there. I'm so curious to find out what all the other prizes in the cosmic lottery for life are and how common they are, right? Just like when you play the lottery, you want to know, what are my odds of winning, and what are my odds of winning all the prizes that are there? And also, what are all the prizes that are out there to win? There's no bigger lottery than will life arise on a planet in this universe.
Right, you are so correct. It's exciting. You kind of bring up. I did not mean to put that one up. I meant to put this one up. Sorry about that. I wanted to get to Carrie Ann Chrysler's question. Are these star systems being observed in our galaxy only? I thought that what you were just saying was a great segue into this.
It is a great thing. So you have to remember, it's easier to find planets around stars the closer they are. We found planets around stars that are a few light years away, that are tens, hundreds, thousands of light years away. The closest galaxy that's not part of the Milky Way is over 100,000 light years away. And at this point in time, that's too far to find planets around stars in them. So yes, the planets we're talking about that we know about are only in our galaxy for now. But when we look at the properties of stars and gas and dust and all the other things we can observe, there is nothing unique about the stars in the Milky Way compared to the stars we see in other galaxies. So we fully expect, yes, they do have planets. They should have planets. We just haven't been able to find them yet. And yeah, there might be one or two where we're like, that's not technically in our galaxy. And yeah, we think that might be a planet. But overwhelming 99.9+% of the planets we know of in our galaxy.
So we have another question from John Hudson. How many exoplanets do we know for sure exist?
Okay, this is good. So when I talk to you about the radial velocity or stellar wobble method, and what I talk to you about the transit method, that's not enough to say that's a definite exoplanet. That's enough to make a candidate exoplanet. You have to detect it via multiple methods to make it a confirmed exoplanet. And you should know that NASA's Kepler mission, which is the most successful planet finding mission we've ever had, it's only about 50% successful. About half of its candidate planets didn't pan out. The biggest culprit turned out to be binary stars. Binary stars confused people, and they were the biggest exoplanet imposter. But yes, as far as how many exoplanets do we know for sure exist, I'm going to give you the confirmed exoplanet number the last time I looked, which is around 5,300 confirmed exoplanets. That number is continuously rising, and NASA and JPL keep an updated exoplanet database that you can query. Any member of the general public can query, and you can say, how many confirmed exoplanets are there? And it'll tell you right now.
So I want to ask you really quickly. I have another question from the audience, but before we do that, you were talking about how when two binary stars are circling each other, it could confuse people. Is it possible for there to be planets around those stars that are circling each other?
Oh, yeah. So any system you have, right? Let's say I've got a binary star system. If the binary is very close together, you can have a planet orbiting far outside of them. If the binary stars are wide, you can have populations of exoplanets. You can have, if this is star number one, you can have exoplanets that closely orbit star one. And then if this is star two, you can have exoplanets that closely orbit stars two. And then if you zoom out, you can have exoplanets that make big orbits around star one and two both. Some people wonder, hey, can you have a star, a planet that goes around one of the stars and then jumps to go around the other star? And can it go back and forth? And yeah, kind of. But those are unstable configurations. So yes, you might have something that does that for a little while, but it won't last. Inevitably, if you are, unless you're in a relatively stable configuration, which means so that you only see one big mass that you're orbiting, either it's because you're very close to one mass and the other one's far away, or you're so far away that these two masses behave as one mass roughly. Unless that's your configuration, you're going to be unstable, which means after a certain number of orbits, you're going to get either kicked out or swallowed. And so that's another type of planet that we see are what we call rogue planets or orphan planets, roaming interstellar space without a parent star at all. We have discovered many of these, and we hope to discover many more. But those are definitely out there, and many models of our own solar system include, hey, maybe in the early days of the solar system, we had a fifth or more giant planet that was kicked out. Maybe back before we had the inner rocky planets, maybe we had other planets in the inner solar system orbiting the sun that were either swallowed by the sun or ejected by Jupiter. So who knows how many planets wind up getting ejected into interstellar space over the history of a typical stellar system like our own. In fact, this is a fun, disturbing thought for all of you. If we run simulations of the four inner rocky planets over the remaining lifetime of our sun, before we become a red giant, in about 1% of those simulations, at least one of the four inner planets gets ejected. So don't be so certain that Mercury, Venus, Earth, Mars is the way it's going to be for eternity.
That's so cool. All right, Carrie and Chrysler has another question. How much do we know about our galaxy and its extent? Does it have an atmosphere? Great question.
You know, this is not something we normally use that word for, but I think it applies. If you think about our galaxy and how it's distributed, right, you're going to say, okay, we've got this disk with spiral arms in it, and it's full of stars. But the galaxy is also full of gas, of molecular gas. That gas gets very dense in the spiral arms, and that's why in the spiral arms, you get gas clouds contracting, and they make these new stars. They give rise to episodes of star formation and these little bursts that create new star clusters. Where does that gas come from? The answer is, well, some of it's always been in the disk, but some of it comes from a giant halo in the galaxy that extends for hundreds of thousands of light years. And over time, that gas gets funneled into the disk, into the spiral arms, and towards the galactic center. So we don't normally think about galaxies as having atmospheres, but they do have reservoirs of gas that exist not just in the plane of a galaxy, but all throughout it. When you have star formation, those stars create winds, they create radiation, and they blow gas back out into the galactic halo. Over time, that gas cools, contracts, and gets sucked back into the galaxy, and then it participates in new episodes of star formation. So when you talk about, you know, some people want to know, like, oh, when our solar system formed, how many generations of stars lived and died to produce the material that we formed from? And the answer is it varies. Some of our material has probably never been inside a star. Some of the material we formed from has been in many, many generations of stars, tens of them. And some have just been in one or two, and some have been in several, and it's all in between. You are made up of the whole collection of all the different populations of gas that mix together to give rise to our star forming region, and specifically that little part of that star forming region that fragmented and made our pre-solar nebula. That's where we come from. And thanks to sciences like astronomy and astrophysics, we're getting real insights into it. I have never thought about a galactic atmosphere, but all of that gas, that's what keeps our galaxy alive. Galaxies without gas, those are dead galaxies. We call them red and dead because when you form stars in a big burst, you produce stars of all different colors, from blue to white to yellow, orange, red. And it's the highest mass, brightest, bluest stars that live the shortest. So you form your stars all at once, and then once time has passed, if you've used up all your gas and you're not forming it anymore, the blue ones die away, and the white ones die away, and the yellow ones die away, and the galaxy you're left with only has those orange and red stars and no more gas. And that's why we call them red and dead. And that's not us, we're alive.
So I know you have a hard stop coming up. So for the last little bit, I wanted to get this one in before I ask you some, like what you think the biggest obstacles are that we have in our future about learning about stuff. But I want to know first, what are super habitable planets?
Okay, super habitable planets is a marketing lie. That's what they are. Super habitable planets was this idea that said, oh, well, we talked about Earth-like worlds, and some of these super Earth worlds, they're bigger than Earth, they have more surface area than Earth, they have more mass, they have more gravity, they have more atmosphere, they have more ingredients. Maybe they're better candidates for being habitable than an Earth-like planet. Well, guess what? We took a look at these planets, and it turns out that if you want to know how big can a planet be and still be Earth-like with a thin atmosphere and liquid water on its surface, the answer is you can only be about maybe 20 to 30% larger in radius than Earth and still have those conditions. So if you want to know how come we don't have any super Earths in our solar system, is we're as super as it gets. Earth is it. Earth is like, this is as big and habitable as a planet can be, because you get a little more large than that. And the only way you can have a solid surface with only a thin atmosphere is if you are so close to your parent star that it boiled all the gas away, that it photo evaporated all that gas away. You would have to be a stripped planetary core like Mercury. That's not habitable. And if you're larger than that, if you're like 40% larger than Earth or twice as large as Earth, now you're in Neptune category. Now you've got this huge, giant gas envelope of hydrogen and helium around you that would crush anything on the surface, just like you and I would be crushed if we went down to the bottom of the ocean without a submarine. Right. Except that wouldn't be under liquid ocean. It would be under your atmosphere, your thousands and thousands of times as thick as Earth's atmosphere. So super habitable planets was sort of this idea that people had before responsible exoplanet scientists came in and said, what? Look at the data. The data tells you no. Earth is pretty super habitable. And if you want to say more habitable than Earth, well, that's a fine idea in theory, but you are writing PR checks that the data cannot cash.
I love that. I love data. I love knowledge and sharing knowledge. And it sounds like we have a lot to look forward to. We're like on the cusp of some major what's the word, like discoveries and ability to see things we've never been able to see before. But what do you think our biggest issues are? What are the obstacles that might keep us from attaining those great discoveries that we're just on the cusp of learning?
You know, science develops proportional to the resources we invest into it. And science suffers when we stop investing resources into it. It takes a long time for it to recover. The biggest obstacles I see are that we have come so far so recently, right? It was only in 1990 that our first world-class space telescope, the Hubble Space Telescope, was launched. I was in 6th grade. That was 1990 that we launched it. Here we are, and where are the fleets of new generations of space telescopes? There was a huge political fight over launching the James Webb Space Telescope. A lot of people wanted to cancel it. I'm just seeing now that NASA's Chandra, which is our premier X-ray observatory, it's the only high-resolution X-ray observatory humanity has, it's in perfect working order. And the president has proposed a budget that decommissions it because it's old. We have the National Science Foundation that is in charge of all of the ground-based astronomy and astrophysics science facilities. And they just said, oh, yeah, we don't need 2 of those 30-meter class telescopes that we talked about. Yeah, we've been working on 2 for over a decade, but let's cancel one of them. One will be enough. And that's what I feel the biggest obstacle is we have this whole wondrous universe out there that we're about to explore. And because we have this political catastrophe on planet Earth happening all over today, where is the funding going to come from? You have Elon Musk. He's got billions and billions of dollars. Is he spending it on astronomy? No, he's spending it fighting astronomers, trying to fill the sky with his Starlink satellites, which are an alarming source of pollution to astronomers. I'm not saying that we don't need internet. I'm saying that, boy, we should probably be doing things sustainably in a way that we don't destroy astronomy and the space around low Earth orbit for generations to come. So for me, that's my biggest fear, is that we stop doing what's brought us to this golden age in astronomy. We stop investing in science, in pushing the envelope in these cutting edge facilities that explore all these different ranges of the electromagnetic spectrum. Why don't we have flagship class gamma ray, X-ray, ultraviolet, visible light, infrared, far infrared, microwave, and radio observatories? Well, radio, fine. Radio, we don't need to build that in space. Our atmosphere is pretty transparent to it. And optical, yeah, we can do a lot of stuff from the ground, which is why building 30-meter class telescopes on the ground is useful. But my biggest fear, what I see happening, is that people are looking at this tiny fraction of a penny of every little bit of GDP that gets invested into science, into astronomy, into this wonder that drives us forward in the world, and says, oh, we don't care. Like, this won't even make a drop in the bucket of the deficit, but let's play the political game and put science on the chopping block. Mm-hmm. And that's what I see happening. And I don't want astronomy and astrophysics in the United States to become what particle physics in the United States became after we canceled the superconducting super collider, which is, yeah, we still do particle physics in the United States, but the United States is not making the big discoveries. We're not on the cutting edge. We're doing little bits of science here and there, and that's it. I don't want us to become like the United Kingdom for astronomy and astrophysics, where, okay, like, I guess we sent that one probe to Halley's Comet in 1986, and we're still hanging our laurels on that. Like, no, come on. We have NASA, we have the National Science Foundation. These are the premier science organizations in the world. and they deserve to be invested in by the wealthiest nation in the world. If we're not going to do it, what do we expect is going to happen? There are all these discoveries out there waiting to happen that we're all super excited about, not just me and the other scientists, but everyone, those of you listening and people who just hear about this, right? We took a picture of a black hole. Holy crap. We went and found exoplanets. Some of them may be inhabited. Isn't that amazing? We are finding supermassive black holes at the center of galaxies. Isn't that amazing? We've seen back farther into the early universe, closer to the Big Bang than ever before. Will we find the first stars, or will we say, oh no, we've seen enough. We can stop looking now. You scientists can go home. Your job is done. That's my nightmare, Sonny.
Yes. It's my nightmare too, and I completely agree with you. Everyone needs to be aware of how important it is to have, first of all, starting in public schools and promoting science and science learning, and moving on from there, so that we have people who are our elected officials who have some type of a knowledge base behind this. That would be awesome. So I know you have a hard stop. Do you have any final thoughts that you want to share with our audience?
You know, my final thoughts, I would say, are there's not just this one idea of, oh, let's look for exoplanets for life in the universe. There are two other ways that we didn't really get a chance to talk about. One is here in our own solar system, we can go to other planets and look for evidence of past, present, or dormant life on them. If we sent humans with a space station and a science lab to Mars, we could know in weeks whether Mars ever had life on it. We could send probes to Venus. Is there life in Venus's atmosphere? Is there archaeological evidence for life on Venus's surface? What about those subsurface oceans on Europa, on Enceladus, on Triton? What about life in the methane lakes and waterfalls on Saturn's Titan? What about life beneath the surface in the groundwater on Ganymede? You know, Ganymede has like 15 times the amount of water. That's the entirety of planet Earth's oceans. Ganymede is almost half water by composition. So look for life here in our solar system. Do planetary science. Go exploring. Let's find what's there. Also, fund SETI. There is the search for extraterrestrial intelligence. We have radio astronomy. Scientists want to build the NG-VLA. Many of you have heard of the VLA. You remember it from Contact, the Very Large Array, huge array of radio telescopes. That thing is 50 years old. Why do we not have a next generation Very Large Array? That was the #1 recommendation for ground-based astronomy in the decadal report commissioned by the National Academies of Science. National Academy of Science, every 10 years, they do this report. And when politics is healthy, NASA and the Department of Energy and the National Science Foundation incorporate these recommendations into their plans. Then they go and ask Congress for the money. NASA's done it. The Department of Energy has done it. National Science Foundation, still run by a Trump appointee, by the way, has not incorporated any of the decadal survey recommendations into their science goals and has not asked Congress for the money to fund these facilities. So I look at this and I say, this is the big threat, is that we have foxes in the henhouse and people who have fundamentally anti-science's agendas plotting the course for science in the 21st century here in the United States. And I'm telling you, this is the road to societal decay.
I agree with you. That was a great final comment. If you guys like the content that we have been showing, please like, subscribe, hit the bell, share, all those good things, or consider becoming a patron. You can go to our Patreon account, and I want to thank all of our current ones: Eric Ozols, Rion, Denise Murphy, Dan D, Michael Wiseman, Cindy Plaza, me, Aaron Coalson, Phil Calderone, Amanda McLeod, and Logan Fisher. Thank you guys so very much. I also want to tell you about our other shows. On Saturday, we have at 3:30 Central, Women, Atheists, Unload. We're having a fundraiser for Black non-believers with Cynthia McDonald, Mandisa Thomas, Tina Marshall, and Maya. The topic is going to be no 19th. Did I get that right? No 19th? Okay, thank you. So our other, let me get my little list up. There we go, thank you. Don't forget to check out our other shows on Skeptic Haven. Tuesdays is Secular Soapbox. Thursdays is With Me. Saturdays, The Global Atheist and Women Atheist Unload. And Let's Talk on Sunday, where you can call in and ask us anything that you would like to. I also want to tell you about, here we go. BajaCon. It's coming up August 9th through 11th. And look at these wonderful speakers. It's in Ontario, Canada. So if you are American, get your passport and get on up there. We love Seth Andrews, Josh Bowen, Hemant Mehta, Forrest Valkai. I mean, look at the wonderful people. Aaron, oh, we just love you, Aaron. I got to get you back on. These are wonderful people. You want to be there. You really do. So be thinking about that. In the meantime, remember to always think critically. Good night, everybody.
Our being knows this is where we came from. We long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.
If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those in authority, then we're up for grabs for the next